He was there when we were there. Should we begin? Is everybody here?
Let me see if there are some lost sheep. Hurting.
Okay, good. All right. Avner Peleg will speak on nonlinear Schrodinger equations.
Okay, so I would like first to start by thanking the organizer for inviting me and for organizing this very nice workshop. So the subject is about using coupled nonlinear Schrodinger equation with dissipative terms to control soliton propagation in broadband optical waveguide systems. And I think the main relation, well, there are several relations to this workshop. One is that the main way to control the propagation or to stabilize it is by linear gain and loss. Another is that we are doing a lot by perturbation theory, but it's not directly, again, PT symmetric problem, although there might be some relation that you may indicate. So this is the outline. I will give an introduction to broadband optical waveguide systems. Then I'll present the propagation model, which is the nonlinear Schrodinger equation, and solitons. I will also describe the perturbation theory for single soliton propagation and single two-soliton collision. And then using this result of this stage, I will construct n-dimensional Lotka-Volterra models for dynamics of the pulse amplitudes or energies. And again, here I will do a stability analysis for these models to stabilize the transmission. And here I think there can be a relation to the subject of non-Hermitian Hamiltonians, although the models are non-Hamiltonians in general. And then I will describe, go back to the subject of coupled and less and describe the comparison between the simplified Lotka-Volterra model and the coupled and less model. So this is the introduction. Broadband transmission is used for enhancing the rates of the overall rates of transmission of information in optical waveguide. So the idea is that we launch many pulse sequences through the same optical waveguide. And the pulses in each sequence, like you see here, are characterized by the same frequency. But the frequencies are different for pulses from different sequences. And therefore, different sequences are called frequency channels, and the overall system is called multi-channel system. And the problem is that the group velocities, because of the difference in the frequencies, the group velocities are also different. So it means that the pulses propagate, all these sequences propagate through the waveguide with different group velocities, and therefore we have collisions because pulses from one sequence pass pulses from another sequence. And because we have many sequences, we can have more than 100, and many pulses in each sequence, then the collisions are very frequent and can lead to transmission error. So transmission degradation, for example, 1 bits turn to zeros. It turns out that one of the processes that become very important in this system is called the interchannel crosstalk, and this is energy exchange in collisions between pulses from different sequences. And physically, there are two main mechanisms to this. One is due to delayed Raman response or Raman scattering in the waveguide. Another is due to a nonlinear loss of gain. And this graph shows an example of the effect of this, what we call Raman crosstalk, or energy exchange in the collisions in optical fiber. in a system with 100 sequences. So what you see is the probability for transmission error. This is the bit error rate as a function of propagation distance for different sequences. And you can see that the bit error rate values are large and they are increasing rapidly. So this is a theoretical calculation of transmission degradation. But to give kind of a more more experimental example, so I'm showing here results of 2 experiments. The first is done in optical fiber. This is for telecommunication systems. This experiment was done with 109 sequences using pulses that are called dispersion meant solitons. What you see here is the log of the probability for transmission error, again the bit error rate, as a function of the essentially wavelength. This is a frequency channel. And you see that you have high values of the bit error rate. The standard requirement is 10 to the minus 9. So you get values that are much higher than the standard requirement. The second experiment is done in silicon waveguides. In this case, it's just an experiment with two sequences. Again, what is shown is the bit error rate, this time as a function of the received power. And the difference between different curves is in the input power. So as we increase the input power, the bit error rate increases. And according to the experimental paper, this indicates that a crosstalk process is involved. In this case, the crosstalk is due to cubic loss. So if we want to explain this experiment, we need a model for the propagation. The model that we use is the nonlinear Schrödinger equation. So in this equation, psi is proportional to the envelope of the electric field. Z is distance, T is time. And the first term, the second term describes the second order dispersion, and the third term describes the nonlinear response of the fiber to the propagation of the electric field. And we can put this equation in the following dimensionless form and then look for solutions. And for many applications, the solutions that are most interesting are the single soliton solution or fundamental soliton solution. So this is given by this expression, and what we see is that each soliton solution is characterized by 4 parameters, which are the amplitude, eta, frequency or group velocity, beta. And then there is the position y and the phase alpha, which enter in the exponential. From the form of the solution, we see that if we take the absolute value, then the shape of the pulse is preserved as it propagates along the fiber. So that is a good property of this solution. And the other property is that if we make perturbation, then the solitons are stable. So because of these nice properties, soliton-based transmission has good advantages compared with other transmission formats. So we are interested in this work in multi-channel transmission, where we have many pulse sequences propagating through the same waveguide. So we need to understand the effect of collision on solitons. So if the fiber is exactly described by the unperturbed NLS equation, the collisions are elastic, which means that the amplitude, frequencies, and shape do not change as a result of the collision. But in reality, there are additional physical processes that act as small perturbation or corrections. And then we are in this picture where the collisions lead to a change in the amplitude, the group velocity, and also to a change in the shape and what we call emission of continuous radiation. So it turns out that one of the effects that becomes very important in multi-channel transmission, broadband transmission with a large number of sequences, is due to a delayed Raman response or Raman scattering. So this is the perturbed NLS, and this is the perturbation term. So when we derive the cubic NLS, then we assume instantaneous response, instantaneous nonlinear response, which means that the response, nonlinear response, is described by a delta function. And then if we do a correction to a delta function plus some correction, we get this expression. Then we want first to find what is the effect of this perturbation on a single soliton propagating the waveguide. So for this, we use a diabatic perturbation theory in which we look for a certain solution in the form of essentially a soliton, but with slowly varying parameters. So this is a soliton solution with slowly varying parameter plus a non-soliton part. It's kind of a radiation unlocalized waves. If we substitute this expression into the perturbed NLS, then we obtain this this equation, which we write here in vector form. And notice that on the left-hand side, we have the rates of the changes in the four soliton parameters. For example, this is the rate of change in the amplitude multiplied by some functions. And these functions are eigenmodes of a linear operator. This is describing small perturbations about the soliton. So now if we, and here is what we obtained by, for the perturbation term. So now in order to calculate, obtain differential equations for the rate of change of the parameters, also for the evolution of the unsolitonic part, what we need is to project both sides of this equation onto the eigenmodes of this linear operator. And this gives us the equation, the rate equation for the change in certain parameters. So for this perturbation, what we obtained that the only effect of the perturbation on the four certain parameters is a frequency shift that is given by this expression. And that was measured experimentally and explained theoretically. The other thing that we want to understand is the effect of delayed Raman response on certain collisions. So as an example, we can consider a collision between a soliton with a central frequency 0. This is kind of a reference, and soliton in the beta channel. Then we use the following assumption: epsilon and 1 over beta are small, which are realistic. The assumption 1 over beta is small means that the group velocity and frequency difference are both large. So these are fast collisions. And then under this assumption, we can show that the main effect of the perturbation on a single collision is an order epsilon amplitude shift that is given by this expression. And we see that this amplitude shift depends on the sign of the frequency difference in such a way that the energy always goes from the high frequency soliton to the low frequency one. And then the magnitude is proportional to the products of the two amplitudes. Then we can also calculate the higher order effects. So how do we obtain this result? We look for a two-certain solution of the perturbed equation, of this equation, as a sum of size and phis, where the size are single pulse solution of the perturbed equation, and the phis describe collision-induced effects. And then we have this ansatz for the form of the size and the phis that is essentially similar to the ansatz for the soliton shape. And then we substitute this expression and use the resonant, the fact that beta is large. So once we integrate over propagation distance, we can neglect terms that are rapidly oscillating with propagation distance. If we do this, then the resulting equation separates into an equation for the collision-induced effects on the envelope of the 0 reference charge soliton, and an equation for this phi beta, which is the collision-induced effect on the second soliton, other soliton. And these equations we can solve essentially analytically by, again, doing expansion with respect to the two small parameters, epsilon 1 over beta. So here's the example for the Raman perturbation. Again, this is the double expansion. And then if we do this expansion, we obtain, this is the equation that we obtain in order epsilon. We can then integrate it and write it in a vector form. So this is the total collision-induced change in the envelope of the reference channel soliton. And then on the other end, similar to what we did for single soliton propagation, we can express this change in terms of the eigenmodes of the linear operator describing small perturbations about the NLS soliton. And then all is left to do is equate these the right-hand sides and again project on the eigenmodes of this linear operator. And if we do this, then we obtain that in the leading order, the only effect on the four soliton parameters is this amplitude shift that I showed before. And then we can compare this analytic expression with numerical solution of the full equation. So essentially, these are the main ingredients that we need to derive the model for a propagation of soliton under many collision and multi-channel transmission.
I assume that beta was very large, so that you showed results close to beta equals to 0.
Yeah, so it turns out that this formula works pretty well even for delta beta or beta equals to 4. But you see that as we get to close to 1, then we get deviations. Okay, so now we can use these results we want to use this result to describe soliton propagation under many collisions. So the first thing that people observed is that if you use the amplitude for encoding the information, then the amplitude pattern is random. And this amplitude pattern randomness, it couples to the amplitude shift. So the dynamics of the amplitude becomes random. And this leads to, as I showed in the first slide, to a bit error rate generation, to transmission degradation. So we want a method to overcome the crosstalk effects on transmission where we encode information in the amplitude. And one way to do this is to encode the information with the phase. This is the parameter alpha that appeared in the exponential in the expression for the soliton. If we encode with the phase, then the amplitudes are all the same, ideally. Therefore, the amplitude patterns are deterministic, so the crosstalk induced amplitude dynamics is deterministic. And then the basic question that we want to answer is whether or not it's possible to achieve stable steady-state transmission with non-zero amplitudes in all channels. So we don't want the amplitudes in certain channels to decay to 0 because that would mean very high bit error rate. We also don't want them to increase to high values because that will essentially couple to other impairment that will lead to high bit error rate. So how do we answer this? We answer this by constructing an ODE for the energies or the amplitudes of the propagating pulses. So this is how we do it. As an example, we can consider a system with 2n+1 channels and frequency difference delta beta between adjacent channels in frequency domain. Then the starting point is the amplitude shift in a single collision. So this is essentially a formula that I showed. Now it's a collision between a soliton from the solitons in the J and K sequences. Again, we assume epsilon 1 over beta are small. Amplitude patterns are deterministic, and the sequences are either infinitely long, corresponding to long-distance transmission, or subject to periodic boundary condition. This would mean that the pulses circulate in a closed fiber loop. And then, in order to construct the model, I need to take into account all the processes that lead to changes in the soliton amplitude. First one is collision-induced amplitude shifts due to the Raman effect. And the second process is a change in the amplitude due to linear, due to waveguide loss, linear waveguide loss, or amplifier gain. So this is where the linear gain and loss enters the picture. And then to construct the model, again, what we need to do is to calculate the change in the amplitude of the soliton, for example, in the J sequence, in the interval between Z and Z plus delta ZC, where delta ZC is the collision distance for the slowest collision in the system. So this is kind of a coarse-graining distance. So if we do this, then we obtain, this is the term due to, so this is the total change in the amplitude. The first term is due to the net linear gain loss, and the second term is the contribution due to all collision-induced amplitude shifts. So it's just a sum over all collision effects. Then what we do is we take the continuum limit, and this leads to the following system of nonlinear differential equations, where we have here the linear term, Gj eta j, and then here we have quadratic term with coefficients that can be either positive or negative. So if we look at this system where we identify this as a predator-prey model with 2n plus 1 species, where 2n plus 1 is also the number of sequences. So we have an analogy between the optical system and the environmental system, where the pulses in the high-frequency channels are the prey, because, as we said, they're in a single collision, they lose energy. The pulses in the low-frequency channels are the predators, since they gain energy. And what we do now is we want to use our knowledge about predator-prey models, or in more generally on Lotka-Volterra models, to find ways to stabilize this crosstalk-induced dynamics. So how can we control the dynamics? We can control the dynamics by controlling the values of the Gj coefficient. And physically, this can be controlled by determining or controlling the values of the amplifier gain of the amplifiers that are positioned, assumed to be positioned along the fiber line, waveguide line. In particular, what we do is we look for an equilibrium state with equal non-zero amplitudes in all channels. This is the ideal situation. If we do this, then this is the expression for the linear gain loss coefficient. If I take all this coupling coefficient to be equal, which means the strength of interaction is equal for all the channel pairs. Actually, it's not, this is not really needed just to get a simplified expression. So just to show that if I forget about these coefficients, then the gain loss coefficient are just a linear function of j. So this means that we need to over-amplify the high-frequency channels and under-amplify the low-frequency channels to compensate for the collision-induced energy changes. Again, we do not assume anything about this. This can be quite general. And this is the final form of the model, which we obtained by substituting this expression back into the original equation. So this is the model that we work with. And now what we want to do is we want first to find the equilibrium state with non-zero amplitudes in all channels. So these are determined by this linear system of algebraic equations. Has a trivial solution that correspond to, in this case, to transmission with equal amplitudes in all channels. And then because the coefficient matrix is anti-symmetric, we can have also infinitely many equilibrium states with unequal amplitudes. So there is kind of a degeneracy in this case. And then for all this, it turns out that for all these equilibrium states where all the amplitudes are, the amplitudes in all channels are non-zero, this function is a Lyapunov function for the model, which means that it satisfies these three properties, and it satisfies for any eta vector, any amplitude vector with positive entries. So it means that we have global stability. Notice that this dVLdz is equal to 0. This will be related to the dynamics that we observed. So this is just an illustration of the prediction of this reduced Predator-Prey or Lotka-Volterra model for 3 channels, numerical solution of the model. So this is a 3D system. It has the usual equilibrium state with 3 amplitudes equal to 1. But again, because of the anti-symmetric nature of the interaction, we get, in the fact that we have an odd number of channels, we get infinitely many steady states with unequal amplitudes that all lie on this red line segment. But the more important point is that if we start with any initial condition, any input amplitudes that are off this red line segment, we always observe this stable oscillation in the Lotka-Volterra model, in the ODE model. So this means that the transmission is stable. And the fact that we see oscillatory dynamics means that it's related to the fact that dVLdz is 0. So far, this was the predictions of the Lotka-Volterra model. But this is a simplified model that neglects higher order effects, so we want to compare it with the full perturbed NLS model. There's a problem with simulating the full perturbed NLS model because the dynamics here, it involves a large number of fast collisions, and it is difficult to track the collision with one field. So in order to circumvent this problem, we therefore work with an equivalent coupled NLS model that has this form. So this is where the coupled NLS model enters. So the psi j are the envelope of the electric field of the j sequence, and now we can track the collisions for each sequence. And it has the same, more or less the same effects as in the original model, second order dispersion, kernel linearity. All these terms here are due to Raman, but it also has the net linear gain loss, where the coefficients are determined by the Lotka-Volterra model. And then we solve this numerically with periodic sequences of solitons. So these are the result for 2 channels. This is just the initial condition. And this is the result that we obtain with the coupled NLS simulations, including a comparison with the Lotka-Volterra model. So we see that we have good agreement between coupled NLS and Predator-Prey model, and stable transmission up to a distance of 2500 in units of the width of the soliton. But after this, the transmission destabilizes due to emission of radiation. And then if we go to 4 channels, essentially it's the same, up to smaller distances. And what happened at these distances, so we start to see pulse distortion, like we see here at a distance of 800. And then if we take the Fourier transform of this pulse pattern, we see that this pulse distortion, which leads eventually to destabilization, is caused by the formation of what we call a radiative sideband. So there is a little bump that belongs to a radiation emitted by this soliton that forms at a frequency of the other solitons. So this is sequence 1, sequence 2. And we see that there is this resonant effect of radiative sideband growth that eventually leads to destabilization. And actually, we can find ways to overcome this radiative sideband growth, for example, by considering frequency-dependent linear gain loss. So this leads to kind of a cleaning of this, or to mitigation of this generation of the radiative sidebands. So far it was just about transmission stabilization. Now I want to show a very quick example of essentially one last slide of the other thing that we can do, which is transmission switching. So this means, in this case, what we can do, we can turn on or off the transmission of one or more of the propagating sequences. So in order to illustrate this, I'm considering perturbed NLS with linear loss, cubic gain, and quintic loss. So it's kind of a special case of Ginzburg complex Ginzburg-Landau equation. And we can do the same analysis. In particular, for two sequences, we have this two-dimensional Lotka-Volterra model. The important parameter is epsilon 3 over epsilon 5. And this is the coupled NLS model. And then we have as in the previous model, we have the desired equilibrium state where both amplitudes are equal, in this case to 1. And the point is the stability of this point changes as we change kappa, this ratio epsilon 3 to epsilon 5. And we can use these changes in stability properties to turn off or on, for example, transmission of the second sequence. So, for example, in on-off switching, we increase kappa from below Kc, K critical, to above it, such that 1, 1 becomes unstable, while this other equilibrium point at S0 is stable. So as a result, the amplitudes of the solitons in the second sequence, they all go to 0, and we switch off the transmission of the second sequence. If we go in the other direction in terms of the value of kappa, then we can turn on back the transmission of this second sequence. And we actually found a way to generalize this treatment to n sequences. Okay, so essentially this is it. So in conclusion, we developed a general method for transmission control in multi-channel optical waveguide system. This method is based on showing that the dynamics of the energy or the amplitudes are described by n-dimensional Lotka-Volterra models, where the form of the model depends on the perturbation. And then by stability analysis for the equilibrium points of the Lotka-Volterra model, we can find a way to stabilize the transmission. And this turns out to work for the main relevant physical processes in actual optical waveguides. So thank you for your attention.
Questions?
Just concerns the effect of the Raman Raman term on the collisions of solitons in the wavelength division multiplex telecommunication systems. Is it practically important or not if you take into regard realistic values of the parameters? Particularly, usually solitons which are user or planned to be used are not very narrow, so that one can expect that the Raman term will be quite small.
Yeah, it becomes relevant, and we have papers on this in the stochastic case where you use the amplitude for encoding. So in order for this to become relevant, you need more than 50 channels. So you need, but once you go above 50, 100 channels, that was used actually in experiments, including in this dispersion method. So it's not conventional, but dispersion method experiment. So it becomes relevant. Actually, this effect is larger than the effect of the collision-induced position shift due to Kerr nonlinearity. But in reality, also these effects actually interact. So they kind of once you include both of them, you get in some cases significant increase in the bit error. But again, the bottom line is that the Raman effect for relevant conventional soliton transmission, it becomes important. We see at above 50, from 50 to 100 channels, it does become important.
So this estimate of 50 or 100 channels is a critical number of the channels? does it depend on what you assume about the typical temporal width of the soliton?
It is very sensitive to the power.
To the power?
Yes. So what we are considering is power of a few milliwatts. That is what was considered.
Peak power or mean power or average power?
This peak power.
Peak power.
Peak power of a few milliwatts, and this is which was what was considered by experimentalists. And with this value, we get that it is important for, let's say, 100 channels.